All right, there we go. So, welcome to the fourth and final chapter in this little adventure. Um, what we're going to do today, again, I'm just going to review a little bit where we were last time and then talk about some real machines, at least the ones that are available to the general public. And what we saw last time, we implemented, we designed a quantum circuit to do Grover, implemented it as a Python program. We believe it's correct, or I believe it's correct, because when I run it on the simulator with any number of qubits, I get the numbers that the math predicts I ought to get. When I run the exact same thing on an actual quantum computer, or at least the ones that are available to the public, the results with 2 qubits are okay, but not great. And then beyond 2 qubits, it's essentially noise, essentially useless. So the obvious question is, hey, what's going on here? What do the researchers in the field propose to do about it? All right, I'm just going to make sure that I really am recording. And yes, okay. So here's what we saw last time. We saw that we had created this example of a quantum computer as a coprocessor of a classical machine. There was an initialization step that put our qubits in some equal superposition state with the Hadamard gates. And then we had a quantum oracle, which selected a particular state somehow. It's a black box that picks and marks a particular state, the one we're interested in finding. And then there was that amplitude amplification step that we devised. And we repeat that evolution block some number of times as determined by that formula. And then we make some observations on the results. So that's the circuit that we designed the last time. And when we ran it, this is what we got. We tried it with anywhere from 2 to 8 qubits. I've tried it with up to 16 qubits on the simulator. And we picked a particular winning state, the one that we were interested in, as a test. And you can see the number of items that we're searching through. That's what that N is there. So, with 8 qubits, we're really looking for the winning state out of 256 items. And it only takes us 12 iterations to end up with nearly 100% probability of getting the right answer. It's not exactly 1.0, but it rounds off to 1.000. There are some digits somewhere beyond those 3. But when we run this on a real machine, either real hardware or a simulator that has a noise model, what we find is with only 2 qubits and 4 items that we're searching through, we only have about an 88% chance of getting the right answer, but you can work with that. But with 3 qubits, what you end up with is practically noise. And beyond that, I didn't even bother trying. So that's the obvious question is, what's going on here? Why is real hardware what you would describe as perhaps useless? Obviously, the purpose of something like Grover and the goal of quantum advantage or quantum superiority is to be able to search a list of, a billion items, where you might need 30 qubits or more than that. So what's going on here? All right, let's talk about real hardware. And I want to talk first about some of the ways that people are actually trying to build quantum computers. And one of the popular ones is to use trapped ions. All right, and these are a form of natural qubits. So here's a, what is SR? Is that strontium or something? I don't remember my high school chemistry, but there's an ion and it's got a ground state that you can use as the 0 state, and it's got an excited state that you can use as the 1 state. And they trap an individual ion in some sort of magnetic or electromagnetic field on a probably a silicon substrate. So the thing about natural qubits, one of their great, or I'd say one of the disadvantages, perhaps, is that you can only work with the molecules that God has provided that you find in the periodic table, and there are only a small number of them. The ones that are outlined in red that seem to be useful for this purpose, and the one that is commonly used is over here. But again, you're stuck with what God has given us. But one of the advantages of natural qubits is that God does not have manufacturing variation, right? Every strontium atom is the same as every other, exactly the same. So its properties, in other words, the energy levels involved, are essentially, essentially a constant of nature. So this is the advantage of using natural qubits, and it's a popular way of building these machines. The other, I'd say, most popular, and there are quite a few what they call modalities for building a quantum computer, but the other one that's very popular, and the one that IBM is using, and I think Google's research is using this one, is a superconducting qubit. And what this is essentially an artificial atom. It's a circuit made on a silicon substrate that is operated at, a couple tens of degrees Kelvin. So a couple of tens of millikelvins is what I meant to say, thousandths of a Kelvin. And this operates kind of as an artificial atom. And the advantage of this is that since we humans design the circuit, we can kind of make what properties we want. The disadvantage, the opposite of the natural atoms, is that there is manufacturing variation. Each one of these things that you put on a substrate has slightly different properties, maybe slightly different energy levels, so they have to be very carefully calibrated. And the way this particular qubit works is, and by the way, another advantage of these is that they can use conventional semiconductor manufacturing techniques, which, as we all know at this point, are extremely sophisticated. So what we have here is a capacitor and an inductor, which makes an oscillator. Now, it's an LC oscillator for those of you, and I'm an electrical engineer, so I sort of remember some of that stuff. And normally, if you put together a capacitor and an inductor, you have a linear oscillator. And the problem with using a linear oscillator, I think also called a harmonic oscillator, is that the energy levels that you create, the quantum states, quantum energy levels that you can create with this sort of artificial atom, are equally spaced in energy. And there's a problem with that. The way these qubits are manipulated is through either lasers or microwave pulses, basically sending photons of just the right energy at the circuit. And the problem with that is that if you're hoping to send one photon and knock it from, say, the ground state to an excited state, but you accidentally send two photons, and if all the energy states are equally spaced, you're going to knock it into a second excited state that you don't want. All right. And it's too hard to control. So what they do is they put a Josephson junction here, which makes the circuit nonlinear. And what that does is it makes the energy levels not equally spaced. And what that means is if you accidentally send it two photons instead of one, that second photon has no effect because the next energy level is not whatever that photon energy is apart from the first energy state. So this is how these things are actually made. These are the superconducting qubits, extremely cold, operating, as I said, maybe at 10 millikelvins, using the conventional and quite sophisticated semiconductor manufacturing techniques. This is what IBM uses, and this is what I think Google is using. Different people use different modalities, but trapped ions, superconducting qubits are the most popular these days. Now, the fundamental problem that plagues all of these machines comes down to the following. Quantum states are very fragile. All right, all the physicists listening to me know that. These highly entangled superpositions, these quantum states, are extremely fragile, and any interaction with the environment can knock them out of this meticulously controlled quantum state and ruin the computation. So on the one hand, we would like qubits that are largely immune to interacting with the environment. And indeed, there are some that are much more immune than others to interacting with the environment. And therefore, their quantum state is going to be less fragile. Unfortunately, the only way to control a qubit is to interact it with the environment. In this case, some sort of microwave pulse. So the less that the qubit interacts with the environment, in other words, the more robust the quantum state, the harder it is to control. And when you get something that's easy to control, it's easy to control because it responds to those photons you're shooting at it, which means that it also responds more readily to environmental noise, and therefore the quantum state is more fragile. And so this situation, which is almost no matter which way you go, you're stuck with this problem. So the qubits that react well to the control react very fast. All right, their gate times, if you will, the time that it takes a gate to react to its control is very short. And when I say very short, I'm talking in the tens of microseconds range. But the quantum state is fragile and doesn't last long. When you have a qubit that's less reactive to the environment, the gate times are much longer, maybe tens of milliseconds, and the quantum state is less fragile and keeps around longer. But in the end, the number of gates that you can successfully control before the quantum state disappears tends to be somewhat limited, almost no matter what qubit that you pick, because the less fragile ones take longer to control. And so the critical number is about how many gates can I have in my circuit before I'm likely to lose the quantum state. And that's really the fundamental problem that we saw with the Grover algorithm that we had, which is we're running on an IBM superconducting machine with pretty fast gate times, but the quantum state also disappears pretty quickly. And so the total number of gates that you can run before you lose the state on the machines that I've used, I'm going to talk about more specific machines, is somewhat limited. Maybe 100 gates or whatever. By the way, when I say, tens of microseconds gate times, somewhere around that, keep in mind that the gate times for contemporary semiconductors, CMOS semiconductors inside your iPhone are more in the tens of picoseconds range. Right. So when I say fast gate times, we're still talking 1,000 or more times slower than, the processors that are running this little Zoom session. So that's kind of where we are. Now, this nifty diagram was put together, and I think MIT put it together, and I've kind of borrowed it from them and recognized them as the source of this. And what this shows is a number of different potential qubit modalities, ways of making a qubit, and what their gate times are. All right, that's the gate speed here, and they're representing this in hertz rather than nanoseconds, but you can convert. And then how many operations you might be able to have before it makes a mistake. All right, and so the best performance is up here, which represents very fast gate times and very long numbers of operations before these things are going to make a mistake. And there are a number of reasons why they might make a mistake. I'm going to get to that in a minute. And so this is a kind of a nifty little diagram, and our superconducting qubits are over here. And you can see they're in the pretty good performance range. The orange dot represents one qubit gates. In other words, the Hadamard gate, the NOT gate, the kind of, the Z gate, the kind of things that we looked at that had one qubit in and one qubit out. And then kind of the lavender colored dot represents two qubit gates, like the controlled NOT gate. And as you can see, the two qubit gates generally have lower performance than the one qubit gates. Trapped ions are over here. So they are slower, substantially slower. This is a log-log scale. So they are something like 100 times, maybe more slower than superconducting qubits, but they also last quite a bit longer, maybe 100 times longer. And the difference for a trapped ion between the one qubit performance and the two qubit performance is pretty substantial. There was some email back and forth after last session about neutral atoms in diamond lattices, and you can see the neutral atoms down here. All right. Again, the performance is really not as good as the two leading examples that I'm talking about. There are some other possibilities, like you can see there's some qubit modalities here where nobody has figured out how to make a two qubit gate. So they show performance for one qubit gates, but nobody's figured out how to make a two qubit gate out of that particular modality. So this kind of diagram, and I'll just erase all this scribble so you can just kind of see the diagram. This is kind of a pretty useful way of understanding what's going on with the various ways that people have conceived and why the trapped ions and the superconductors are the ones that people are pursuing most aggressively right now. You can see, by the way, if you look at number of operations before error, the superconducting qubits, it's about 1,000 operations for the single qubit gates and about only 100 operations for the two qubit gates. So you can see why, Grover has a lot of gates involved in just doing a small number of qubits. And so it's pretty clear what's going on here. And what happens, there are several ways that a qubit can essentially make a mistake. And the first is that due to environmental influence, the amplitude of the quantum state can change. Think of it maybe as a flip from the excited state back to the ground state, or maybe the other way around, from the quantum logical 1 back to 0 or whatever. And there's a time called T1 that quantum researchers talk about, which is kind of the average time of a qubit to lose the proper quantum amplitude. And then there's another time called T2, which is the time to lose quantum phase. And quantum researchers talk about T1 and T2 and what those times are. In a minute, we're going to look at some of those times on some real machines. And then there's also a question of noisiness. Sometimes these gates will simply misbehave, which people describe just as a manifestation of noise. And we're going to take a look at that. But that's the situation that we're dealing with in terms of actual devices used to make quantum, or at least gate model quantum computers right now. All right. Any questions or comments about this before we go on? All right. Yeah.
Bill, sure. What's the red dotted line?
What is the red dotted line?
You know?
I don't know what that is. I'm sort of guessing that that's maybe a line of minimum viability.
Yeah.
Or it may be, actually, there's something called the quantum threshold theorem that we are going to get to. Maybe that's the threshold, because there's this wonderful theorem that we're going to get to at the end of this at the end of today, which says that as long as the gate fidelity is above a certain amount, then you can build error correcting. And so that's what that red line, it's not labeled on this diagram, but it may refer to that quantum threshold. And we're going to see what that is at the end of the talk today. But good question. All right. So this is an IBM Quantum Computer. you can kind of see the scale of it all. As I said, these are refrigerated to within a few millikelvins of absolute zero. You can see the internal complexity of one of these things. It's a pretty remarkable engineering achievement. So what I'm going to do now, I'm going to unshare. I'm going to unshare this particular screen and share another one. And I'm going to share here we go. Okay, so I'm right now logged in to IBM's Quantum Experience. And I'm going to show you a couple of things about using one of the machines that are publicly available. Again, IBM makes some number of machines publicly available. And in fact, you can sort of see what that is. If we go to, let's see here, I think that one. Yeah, okay. So each one of these machines where it says systems, each one of these machines is an IBM quantum computer somewhere in the cloud that you can access. You can run programs on. All you need is to sign up for an account. It doesn't cost anything. And I have mostly used IBM Santiago, that one, because it is, by looking at its performance numbers, it is the most capable of the public machines. In fact, you can see I've used it. I've run 5 jobs on it. And you can see some of those times I was talking about here, right? Let's see, we'll look at in a minute about the gate delay time. Yeah, but there's the average T1 time, about 128 microseconds before, on average, before you lose quantum amplitude, and the T2 time being about 137 microseconds. So that's what this particular machine provides. You can see that it's got 157 jobs pending, and that's probably several hour wait time. If you submit something to IBM Santiago, you're going to be at the back of a 158 job queue. And as I said, it's probably several hours to run through that. I've seen the Santiago queue get up to 5,000 jobs, which would probably be several weeks of time. And we're going to be looking at this in more detail. There's a number here. By the way, this machine, as you can see, has 5 qubits. And there's a number that IBM provides called quantum volume. That number is over here. All right, quantum volume. And this is IBM's measure of kind of how big a quantum program you can run successfully on this machine. I looked up how they define quantum volume, and it's a very complicated empirical measurement that I won't even begin to try to describe, other than to say that the various quantum computers that they rate. There are these 32 quantum volume machines. There are some 16 machines, some 8 machines. These always turn out to be powers of 2. I'm not quite sure why, but the 32 quantum volume machine is kind of the best that you can get as a member of the public. Now, if I go to, just as a kind of little demonstration, Quantum Composer. So this nice little IBM feature allows me to design a quantum circuit and submit it to one of these machines. Now, I used a Python program last time, because what I wanted, I wanted a fairly sophisticated program, something way more complicated than I can make with the Composer. But for example, let's just make the Bell state that we talked about a couple of sessions ago. So I drag a Hadamard gate, and then I drag a controlled NOT gate, looks like this, all right? And what this makes is an equal superposition. You can kind of see that in this little picture here. And if I scroll, let me just scroll this thing here. So yeah, you can see there's kind of a histogram of possible states. So there's like this is the quantum amplitude, which is square root of 2 over 2 amplitude, that it's going to be in the 0, 0 state versus the 1, 1 state. This is a highly entangled state. And so this quantum composer lets you make certain kinds of simple circuits and tells you how they will perform. And then it shows you what the actual code would look like. All right, because it translates this circuit into actual code that can run on a quantum computer. And you can actually then just submit this to either their simulator or to one of their actual computers and run it. Right, so that's what you can do with the quantum composer. It's got all these gates. You can drag them onto the diagram. You can look at what the result would be. This web-based simulator can only handle like 5 qubits or something like that. As you know, the amount of processing power that you need to simulate a quantum computer grows exponentially with the number of qubits. So this online thing does not allow very many. But that's an example of how to use this thing. Now let's look in a little bit more detail at one of the quantum computers. So as I said, I've used IBM Santiago. Let's look at that one. So first of all, you can see it's got 5 qubits, and this is the topology here, right? This little diagram in the lower right-hand corner, and the topology just says, how are these things interconnected? And different machines have different topologies, different connection between the 2 qubits. And there are a number of useful things that it provides, including, as I said, the T1 times, the T2 times, again, somewhere in the 130 microsecond range. Tells you the basic gates. This is the universal gate set that I was talking about. And from these 5 gates, you can make any possible quantum gate. You can see what the average error time is for a controlled NOT gate, which is about it's about 6 times 10 to the minus 3, you know, so it's like, I don't know, 6 parts in 1,000 is the error rate. And then there's also an error rate for observing the thing, which is even a little bit higher. You can begin to see why there's a little bit of trouble here, right? Because these error rates are fairly substantial. When you think about the error rate of a classical computer, it's almost indistinguishable from zero. You know, I mean, a classical computer, you know, is probably running, you know, a trillion bit operations per second and can probably run for a year without ever making a mistake. I mean, it's really stunning. And I'm not talking about communication that can make mistakes, but the actual core CPU, classical CPU, is really quite stunning in its non-existent error rate. And so these are fairly substantial error rates. So you can look at, for example, the qubit gate times, which again, they measure in frequency. And this is in a gigahertz frequency. And the minimum, that's 6.4 gigahertz maximum, 4.6 maximum 4.8. So it varies from bit to bit. Remember I said that due to manufacturing variations, these bits don't quite behave all the same. There's a variation in the average frequency at which they operate, variation in the average error, all right? And we can look at, for example, the T1 times and see that they vary from 75 microseconds to 150 microseconds. The average T1 time is 128, but there's some variation there. Some of them not so good, some of them much better. So this is what you're working with an actual quantum computer. There's a graph view. You can look at this is the frequency of the 5 qubits. Here's the T1 time of the 5 qubits. So it gives you all this wonderful information about the machine that we're running on. There's a view of the 5 qubits that shows T1, T2, operating frequency, readout errors. So when I said I liked running on IBM Santiago, what is, I just looked at these numbers. And they seem to be, of all the machines that are available to me, they seem to be about the best. And so that's why I liked running on that. And that's probably why their queues, the wait time to get on one of these machines can be so long. So that's IBM Santiago. Now, what I want to do now is look at all of the machines that IBM has, right? And these 128 quantum volume machines, these 64 volume machines. Here's one. Look at IBM Montreal, all right? And IBM Manhattan, for example. Let's look at IBM Manhattan. It's got a quantum volume of 32, but it's got 65 qubits. Take a quick look at this. There's IBM Manhattan. That's the topology there. That's how it's interconnected. And if you look at the times, yeah, the T1 and T2 times aren't really all that good. They are generally worse than that IBM Santiago machine. I think the reason why this gets a better quantum volume is that because it's got so many qubits, it can execute a lot of gates in parallel, which means that even though we're losing quantum state fairly quickly, because we can execute gates in parallel, we have the ability to do a bigger quantum job. So that's IBM Manhattan. And let's look at the best machine they've got here, a volume of 128. This is IBM Montreal with 27 qubits. These are all named after cities, and it may be that the quantum computer is actually in that city. I'm not sure, but maybe it is. In any event, this is their top of the line, 128 volume, 27 qubit machine. And notice the T1 and T2 times are really no better than the one that's available to me, that IBM Santiago machine. Again, I think what makes this machine have such high quantum volume is that its topology, a number of qubits, allows the gates to be run in parallel. And so that's what this thing is all about. Now, when I submitted my job to run Grover on IBM Santiago or one of the various machines, you can see some of these results here. So let's look at this job that I ran 2 months ago. All right, and you can see the machine that this ran on. I wanted to run this on Santiago, but it was too busy. So I ran it on a different machine, and it took, it was in the queue and running for 38 minutes. That's how most of that time was waiting in the queue. And you can see what happened. It was created. It was essentially compiled. It was in the queue for 38 minutes, and it ran for 7.5 seconds. And that means that it ran my program 1,000 times. And these were the results that I got. And again, the winning state here was the 1-1 state. And you can see there was about a 63% chance that I was getting the right answer on this particular machine. And all these other answers are wrong, and they represent noise. And what I mentioned about running Grover is that if you take a particular answer, you can then run it through a classical oracle to validate it. And if it's not validated, in other words, if it was one of these error states, you can just try it again. So this is an example of running what IBM produced when I ran the thing. Now, this is the diagram, the circuit diagram. Now, this is not the circuit diagram that we created. This is the circuit diagram translated to the 5 base gates that make the universal gate set of this machine. And so this does not look all that familiar. You can see how many gates are involved in the translation. All right, we used a lot of Toffoli gates, those 3 qubit gates in designing this circuit, but those don't really exist. Those have to be made out of 2 qubit gates. And so that's what the translated circuit diagram looks like. This is what the essentially assembly language looks like, converting to what are essentially raw instructions, like, for example, SX is a square root of X gate on qubit number 1, and there's a rotate Z gate by some number of radians on qubit number 1. You can kind of see what this looks like. So this is the circuit now translated into quantum assembly language. And there's a kind of another version of that. I'm not sure these two versions have different purposes. But basically, that's what you can do as a member of the public over at IBM. You can create circuits in their composer. You can see what they do. You can inspect their state. You can submit jobs either to the simulator or to a real machine. You can get results, and it's pretty cool. It's a pretty nice thing to be able to do. And what IBM is trying to do here is that they're trying to get a broad research community to play around with this stuff in the hopes that eventually, people will contribute to the state of the art, and eventually there might be some actual commercial value in all of these outrageously expensive machines that IBM and others are trying to put together. So those are the real machines that I've been working with. The results that I got, and by the way, let's just take a quick look at one of the 3-qubit ones that I ran. So here, for example, there's a 3-qubit run on an actual machine. Yeah, there we go. And you see, it's just noise, right? The winning state, the true state is right here. It's just noise. There's nothing there, right? And the reason there's nothing there is just too many gates, right? There's just too many gates. By the time it gets halfway through all these gates, the quantum state is destroyed, right? Again, this is not the most efficient implementation of a 3-qubit Grover, and it is not the best machine IBM has by a long shot, but still, to be commercially useful or to be useful for any purpose, we'd need to be able to run this with 30 or 40 qubits, not 3. All right, so we're obviously a long way from that. Even the top of the line machines really don't have what we want. All right, so what I'm going to do now is go back to, let's see here. I'm going to stop sharing that one. Let's go back to here. And that's my quantum demo. All right. And now, yes, there's a summary of the machines that we looked at. And you can see these two are available to the public with 5 qubits, different quantum volumes. Montreal is the one that we looked at. And if you look at the gate times are around a little under half a microsecond. And the T1, T2 times you can see there's Santiago. And again, their fancy machine, Montreal, is really about the same in terms of all of its properties are about the same as the 5-qubit 32 quantum volume machine. The main difference, as I said, is that I think it can run more gates in parallel, and I think that's why it gets a higher quantum volume. So it's interesting that the basic properties, although IBM keeps advancing the state of the art, the basic properties, these basic properties here, have hardly improved from Santiago to Montreal. I think that reflects, again, this fundamental limitation that the only way to make, the only way to do more work is to either make the gate run faster or to have the quantum state hang around longer. But those two things move together. The faster you make the gate, the more susceptible the quantum state is to outside interference. And so there really hasn't been improvement here. And the only way we're going to get anywhere with this stuff is to look at quantum error correction. And this is the big topic now in the research community. All right, so quantum threshold theorem. And the idea here is, and I'm quoting here from Wikipedia, because they expressed it about as well as I know how to express it. So basically, any quantum computer with an error rate below a certain threshold, and I think that's what that red line that Liz pointed out earlier, can produce an error rate that is arbitrarily low. And the idea is that you make logical qubits out of physical qubits. using an error correction scheme. All right, so the idea is to make a reliable logical qubit from a flock of unreliable physical qubits. And so this is an error correction scheme. I think the word flock is something that I just made up. I don't know what they actually call a set of physical qubits. So how does quantum error correction work? Well, the short answer is I don't really fully understand it, but I can give you some ideas on that. Normally when you're building error correction into a classical circuit, the idea is that you have some redundancy, right? Maybe a parity bit or more sophisticated redundancy. So you look at the current state, and if the redundancy checks don't match, then you have a problem. And if the redundancy is sufficient, you can correct the problem, right? Those are error correcting codes. And so, for example, hard drives will use error correcting codes because, there are errors in reading bits off of a moving magnetic medium. Communicating packets on the internet will use error correction. And that's the way it's done in classical computers. There is, however, a serious problem with quantum computers because you can't measure a quantum state without destroying it, right? So how do you do an error correction of a quantum state if you can't measure it? All right. And so clever people have kind of figured out a way to do that. And then what you do is you introduce redundancy that allows you to push a quantum state from an erroneous condition into the condition it's supposed to be without having to actually measure it. And that's the trick there. All right. And then the idea is that you entangle a bunch of logical qubits based upon physical qubits that have an error rate that's above this fancy quantum threshold. And by nature of this entanglement, you can then, and again, the math is not something I've studied in any detail, so I'm really giving you kind of a vague explanation, but the idea then is that you can nudge it back to the state that it's supposed to be in without actually having to measure it, because if you measured it, you would destroy the state. And so quantum error correction is quite a bit nastier than it is in classical computers, but there is a theory behind it. And how much practice there is behind it is not clear. I'm not sure that there really are any current examples of a machine that can do this, although there are people who are really working on it, and it's clearly necessary, right? There is, as best we understand, there is simply no way to build a useful gate model quantum computer without significant error correction. In other words, without making these logical qubits out of a number of unreliable physical qubits. Now, the nice thing about using either trapped ions or superconducting things is, they're really small and they're made on, they're made with contemporary semiconductor processes. So it's certainly practical, perhaps, to put on a substrate, 1 million physical qubits and turn them into logical qubits, right? That ability to manufacture lots of things is something that we are really good at right now. And so the question is, with the kind of error rates that we seem to be able to create, how many physical qubits do you need to make a reliable logical qubit? And the best guess is about 1,000. That's a humongous number. About 1,000, or at least 1,000. All right, current estimates. And again, I don't think anyone's ever done this, but people have done the math, and they've got some very smart people, very sophisticated things. So the idea is, if you want to make a machine with 1,000 reliable logical qubits, you're going to need a million physical qubits. But that's not completely crazy. Right? I mean, people can put 1 billion transistors on a chip. So the idea of making 1 million physical qubits on a chip is not completely crazy, but no one's ever done it. Right? No one's ever done it. People are working like crazy on it, but no one's ever done it. And so this then is my best understanding. And again, I'm hardly an expert. I've been studying quantum computers. I started around Christmas, so I've been at this for 5 months, I'm hardly an expert, but the best I can figure is that this is the state of the art right now for gate model machines, right? The kind of machines that people talk about being able to, crack RSA encryption by factoring large numbers, is that they are extremely noisy. You can make a machine with a couple dozen, maybe, 40, 50 qubits, but you can't do much with it. And in order to do anything remotely useful, we're going to need sophisticated error correction, and we're going to need something like 1,000 or more physical qubits to make a reliable logical qubit. That, as best as I can tell, is where we are right now. All right. Questions about this so far?
Bill, I have a question. You showed us those images of those large, really cold chambers, presumably that will house the superconducting qubits on their substrates. Do you understand that they have multiple copies of 5-qubit circuits in there, or there's just one 5-qubit physical thing in that big tank?
Yeah, I think there's just one.
Okay.
And I think the complexity of that is the control, because you've got to control this with microwave pulses, and you got to have readouts. I mean, again, I'm hardly an expert on, why those machines are so humongous. And obviously there's a lot of refrigeration involved.
Right. Right.
But yeah, no, I think those machines are just, 5 or maybe as many as, 65.
That's right.
qubits.
One of them was that.
So there's this tiny little thing, and then there's this massive amount of control and cooling around it. That's my understanding.
Yeah. Thanks.
Yep.
So just a takeaway. I was just trying to make sure I have the right takeaway in my head, which is that every reliable logical qubit you have like doubles your computing power, or sort of gives you it's like exponential growth in your computing power.
Correct.
Yeah. So this is actually, needing 1,000 physical qubits for one logical qubit, I mean, assuming the technology gets there, is actually, it's not defeated before it even starts. Cause like if you needed 100, if somehow you could put 100,000 physical qubits to make 100 logical qubits, then you could actually get a lot of computing power.
That's absolutely right. In other words, a machine with 100 reliable qubits is a very powerful machine. Very powerful. It's beyond, the maximum that can be simulated with a classical computer, is somewhere around 40 qubits. Beyond that, the computation gets crazy. So if you can put together 100 qubit machine with reliable qubits, you've got a very powerful machine. Okay, so this is not something that's completely crazy, but it's an interesting question as to where this is. A lot of people that I've listened to talk about this as well. We're kind of in the early stages of quantum computing, just like we were like in the 1940s and 50s with stored program machines, and I don't think that's a great analogy personally. I mean, and I'll tell you, the early stored program machines, we're talking 1940s, 1950s, the kind that, von Neumann designed, they were extremely primitive computers, right? They had, I don't know if you know what the main memory was like on those machines, but they used acoustic delay lines in vats of mercury for memory, right? So you take a vat of mercury at a constant temperature, you put essentially a transmitter, an acoustic transmitter on one end and an acoustic receiver on the other, and the bits are stored by sound waves circulating around these vats of mercury, right? And it took up an entire room. That's what they used in the 1940s. And however, those machines were useful. They could perform calculations that nothing else could. Right. So from the very earliest vacuum tube, acoustic delay line stored program machines, they were useful and powerful compared to what they had. Right. There are no, as far as I can tell, there are no useful gate model quantum computers in the world. Right. None of them are. So to me, it feels a little different than the early days of stored program machines. And the question I have to ask myself, because I'm an engineer, And so the question I ask myself is, what the engineering challenges in building a practical quantum, gate model computer, are they the kinds of things that, okay, we can see how to do this, 100 qubits, 100 reliable qubits, great. We need 100,000 physical, but we can make that on a chip and whatever. Okay, great. But that's possible. But is this like hydrogen fusion? The kind of thing that's theoretically possible, but is such a difficult engineering challenge that nobody's been able to build a practical hydrogen fusion generator ever. And we keep talking about it. I don't know. Can you really? Let's say I've got 100 qubits, right? So I've got 2 to the 100th. I've got a state vector with 2 to the 100th components, and each one of those components has a magnitude and a phase. Okay. Can you really, as an engineering, yeah, theoretically the math works, but as an engineering proposition, can you really do that? Does the universe really allow you to do that as an engineering proposition? I don't know. And if you talk, there's so many very smart people and companies and money being thrown at this that I kind of figure, okay, yeah, maybe I'm a little skeptical, but those guys probably know what they're doing. But still, right? This is not like, John von Neumann fooling around with vacuum tubes in 1946. This is a little different than that. And can these machines actually be built? I don't know. I really don't know.
It's part of the reason I asked, because I do remember seeing some headline a year or so ago from I think it was a mathematician or a theorist saying that like having some reasons why he thought quantum computing would never get there, would never become feasible. And I don't know I don't remember at all what his arguments were, but I just wondered if it was something like what you're saying.
Yeah, I didn't read that. And again, it is not unreasonable to be skeptical. And indeed, skepticism is one of the most important attributes of science and engineering. So the fact that, people have got the math figured out, but nobody's built it yet. A lot of people are trying. And just because it works on paper doesn't mean you can make it work in practice, or doesn't mean you can make it work in practice in 10 years. And there are a lot of people, you read a lot of articles about, oh, this is just around the corner, and IBM's got a plan for like doubling their quantum volume, kind of like a Moore's law kind of thing. They've published this. They want 100 qubits, by like 2023. And hey, these are some awful smart people with huge resources. So it's not crazy to believe them. I think it's also not crazy to be a little skeptical. So that's my experience. And that's really, that's what I've got to say on quantum computing. I really, I really enjoyed trying to put this together. I got interested in this, as I said, over Christmas. I'm getting old, and they say that you need to do something to keep your mind active. I'm 67, right? Says, okay, I'll learn quantum computers. That ought to do the trick. And I put this together kind of as a way of proving to myself that I understood it well enough to explain it, and hopefully I've in some measure succeeded at that. Hopefully, and I really appreciate everybody taking the time to join this and participating in this little experiment of, is it possible in 5 hours to present this stuff at a technical depth that is satisfying to serious people? You can get a lot of summaries, popular summaries that aren't very deep. And then you can listen to the experts in the field and not understand a word they're saying. And I'm kind of shooting for something somewhere in the middle. So hopefully it's all worked out. And I really appreciate everybody's attendance.
It's been really interesting. Thanks. Makes me think of, I just got off an atomic, molecular, and optical physics NSF panel. So for example, the strontium ion trapping stuff, people had gas phase examples of some of that single atom, single item control, and this is the way research works. And some of that seminal research gets translated into these applications. So that community, optical physics and atomic and molecular physics, has a whole sector now on investigating potential physical systems. One of the things I think is really intriguing is, rather than building up a big state vector space, ion by ion, can you actually explore a physical system that has that dimensionality of physical space already built in? I mean, it's a different challenge to figure out initializing such a thing, because I don't know how, so there's a lot of work on using lasers to create large arrays where you would put all these single ions in there and controlling and protecting them, controlling their interactions with one another through using applied fields and everything. But anyways, it's, as you said, the federal government, through funding this basic kind of research, is also funding these kind of very foundational ideas around quantum computing.
Yeah, it'll definitely be interesting to see how it develops. I'm glad to understand something of the theory behind it. It'll be an interesting thing to watch. I mean, if you remember the first during the first session, I put up the headline of a Newsweek article, where everybody's all panicked about security and competition with China. I think I'm not worried. At least for the next 10 years or so, but we'll see how it goes. I know that, for example, Microsoft is working with a qubit design somehow based, I can't remember what they call it. There's some fancy word for it that I can't remember, but the idea is that this particular qubit would have spectacular noise properties and are very immune to the kind of noise. And somebody, I remember reading a remark about this, that this particular qubit exists only in somebody's research notebook. So that's people are working on this. We'll see. All right. Any other closing comments or discussions?
Just thanks again. That was really,
Thank you so
really
much.
appreciate you taking the time, putting it all together. It was fun.
Okay,
Really
great.
intriguing. Thanks, Bill.
Yeah,
Yeah.
so I'll post this final recording, and I think at some point we're going to put these recordings up on the computer science department website so that anybody can look at them.
Yeah.
Feel free to share the recordings with anyone you want. And thanks all. This was fun.
Thank you.
Thank you, Bill. Appreciate it.
All right. Take care.
Bye.